Good afternoon, everyone, and welcome to our second virtual lecture as part of Lancaster Water Week 2020. My name is Kelly Snavely, and I am the Director of Marketing Communications for the Lancaster Conservancy. Tonight, we are joined by Jeff Beloga of Becker Engineering and Charlie Miller of Blue and Green Insights to talk about protecting New Holland's water supply while developing a native tree arboretum and park for the community to enjoy. Tonight's presentation is being recorded and will be shared with everyone who pre-registered within the next several days. We welcome you to use the chat button at the bottom of your screen to chat with each other and our panelists. Please use the Q&A button to share any questions you might want Jeff or Charlie to answer at the end of their presentation. I also would like to take a moment to share about some of the other virtual lectures that you can attend this week. Tomorrow at noon, we are joined by Turkey Hill Dairy, the Alliance for the Chesapeake Bay, and the Maryland and Virginia Milk Producers Cooperative to talk about the work they are doing to implement clean water best management practices on regional dairy farms. Other lectures coming up this week include History of the Conestoga River, Pollinator and Rain Garden Design, and the Hidden World of Stream Insects. Please also consider taking the Lancaster Water Week Pledge, a commitment to take 3 simple action steps in your life to help clean up our local streams and rivers. With your pledge, you get a free kit, which includes reusable totes stuffed with educational materials to help you achieve each action step, and a free native tree or shrub. To sign up for an event or take the Lancaster Water Week Pledge, please visit lancasterwaterweek.org. Finally, Water Week is only possible because of the very generous support of our sponsors. There are local organizations and businesses that are passionate about clean water. Through their generous support, we are able to host these events, and they've helped us contribute over $120,000 in grants to implement shovel-ready projects here in Lancaster County to help clean up our waterways. Turkey Hill Dairy has been our presenting sponsor since we were founded in 2017. Today, I also want to recognize the Campbell Foundation and the Chesapeake Bay Foundation for their Keystone 10 Million Trees partnership, the generous donors of the native trees that you will receive in your Water Week Pledge Kit. With that, I want to introduce our first speaker tonight. Jeff Beloga has over 25 years of geology experience, including geologic and hydrogeological investigations. Developing, I apologize. Here we are. Developing large volume supply wells, groundwater resource planning, environmental consulting, soil and groundwater contamination remediation, and hazardous geology studies. A Penn State graduate and Lancaster, PA resident, Mr. Beloga possesses knowledge and experience interfacing with federal, state, and local regulatory agencies, including the US EPA, PADEP, Susquehanna and Delaware River Basin Commission, and others. Thank you, Jeff, for joining us tonight.
Okay, thank you very much, Kelly. I am here with Kyle Postlewaite of Becker Engineering. I'd like to talk to you tonight about well development as it relates to the Groff Memorial Park and some of the reasons why we put it there, as well as the New Holland Borough Water Authority water system and water resources. Currently, the New Holland Borough Authority operates 4 wells in 3 discrete locations. That's important for wellhead protection and well operations and maintenance. If one of their wells would go down, go bad, a pump go bad, a shaft go bad, we can switch to a different well. Currently, the wells are all positioned and operate at a capacity where they can supply the entire system by themselves. So when we were looking at where to put well 5, some of the things, or the new well, some of the things that were important were having a separate wellhead protection area so that if it was a contamination problem that would possibly impact the well, this well would have a different sub-watershed feeding water to the well and would not be so susceptible to the same groundwater contamination as possibly another well that may have an issue. But with that, New Holland is permitted by the Susquehanna River Basin Commission because they do serve over 100,000 gallons per day. And they're permitted to serve a maximum capacity of 1.65 million gallons per day, or 1,146 gallons per minute of potable groundwater. Currently, they have, like I said, 4 wells, 3 locations. Wells 1 and 2 are in 1 location. Wells 3 and 4 are in 2 discrete locations. We did have a map of where the wells are at, but since 9/11 in those times, they kind of got away from sharing where water sources are. I wouldn't say they're top secret, but they're just not publicized anymore. But with that, New Holland decided to plan for a new well, which would be well 5. And really, it wasn't for additional water so much as it was for redundancy, and redundancy for impacts that may occur to other wells through groundwater contamination and or maintenance concerns. 1.65 million gallons a day is enough to supply the New Holland Borough Water System Authority. And as a matter of fact, each well by itself can supply the authority the needed water per day. However, if one well would go down because of a contamination issue and another well would go down because of a maintenance issue, very quickly you could be in a position where you're relying on 2 wells, which still is a good position, but you can see how redundancy in a larger water system is very important. So the addition of well number 5 would provide flexibility to the water system with respect to maintenance of potential water quality impacts with their current water demands. And it would also help for future water demands in a build out for new development within the borough and the surrounding communities. New Holland Borough does supply the New Holland Borough itself, as well as Earl Township and East Earl Township. This slide shows you the location of the well within the Groff Memorial Park. Like I said, it's one of 5 wells in the borough. It's on the outlying edge of the borough, right on the border of Earl Township. The park is a community tree park. It's a pretty passive park. Nothing really happens there. It's a walk-through park, picnic table, I believe. You can go ahead. Thank you. So what we did when we sited the well is we looked at the groundwater recharge estimates in the area. And for well number 5, it's in the same watershed as well as 1 and 2. So if you look at the table in front of you, it has 3 different geologic formations that the 3 wells are located in, wells number 1, 2, and 5. Because all 3 wells are considered in the same watershed, although 1 and 2 and 5 are in separate sub-watersheds. We looked at the watershed as a whole, and the three formations would be the Zook's Corner, the Buffalo Springs, and the Stonehenge Formation. They each have an assigned contributing area to the wells based on topography. With that area within the topography of the watershed, we can come up with the amount of precipitation that falls on that ground in a year, and come up with the amount of recharge. Theoretically, that would go to the aquifer that's feeding that well. Now, based on geologic structure and other things, that may or may not be an entirely accurate representation of the amount of water availability, but it's a kind of a cookie cutter place to start when you're siting a well. But with that, we take the amount of area and the amount of rainfall that comes to a well, and then we look at the 1 in 10 year drought recharge for that area. So that's kind of the worst year you would have in 10 years for precipitation, and we would use that number for planning. What that does is that pretty much says that well will have a safe yield if it's designed based on those numbers in a worst case scenario, and that's why we use the 1 in 10 year drought recharge. And for this watershed that has well number 1, number 2, and number 5, the available 1 in 10 year drought recharge is about 2 million gallons per day, or 2.1 million gallons per day. You can go So what we did, we had the drought year recharge of 2 million gallons a day. We looked at wells 1 and 2, which withdraw about 1/2 of a million gallons per day. So if we look at the available water, which is the precipitation on the area, the geologic formations, we have an available water of 1.5 million gallons per day. We wanted to add an additional 500,000 gallons per day with well 5, which took us down to 1.069 of remaining available water, or we were utilizing 48% of the 1 in 10 year drought recharge for the aquifer. With that background, we did drill well number 5. It's a 10-inch open borehole well. It has 211 feet of steel casing in the well. So it's a hole drilled in the ground. You install steel casing. So for the first 211 feet, really no water can enter the well. Then the well is an open borehole in bedrock from 211 feet to 420 feet below grade. How you build a well, particularly in the valleys of Lancaster in a carbonated setting, is fairly important to protect from surface water impacts and influences. You never can guarantee getting away from surface water impacts and having treatment issues, but a carefully planned well, carefully drilled test well, you can limit surface water impacts. So that's Borlago well number 5 and how it was drilled. So after we drilled it, we began to pursue the Susquehanna River Basin Commission to permit the well for the volume we had wished to get. Couple things about permitting. In Pennsylvania, for a public drinking water supply, there's 2 basic hurdles you have to overcome, not hurdles, but regulatory requirements. Susquehanna River Basin Commission, they really kind of focus on water quantity. So they're looking at water quantity impacts, ecological impacts, impacts to other users, things like that. So when you drill a well and you test it, the one aspect you're looking at is the water quantity and impacts to other users in the environment. River Basin regulates that. Water quality concerns are more closely regulated by the Department of Environmental Protection. And they're looking at, the water quality of the well, how you're treating it, treatment systems that are put in place, the amount of redundancy you have in treatment systems and safety factors and things like that. That does overlap. The River Basin does in fact look at some water quality issues, and the DEP does in fact look at quantity issues. For non-consumptive uses like this, where the water is used and returned to the same watershed that it's taken from, is a non-consumptive use. Susquehanna River Basin regulates uses that are over 100,000 gallons per day, which is approximately 70 gallons per minute on a 24/7 total time frame. So the well was drilled, and when we got ready to do complete aquifer testing, we did complete that and start in June 2018, an aquifer test. Some kind of tricky things with well number 5 is we did have some treatment issues. Whenever you treat and discharge water to the surface, you need to treat for all the potential contaminants in the water. So the slide you see in front of you is actually an air stripper, which removes volatile organic compounds that are in the water. Well number 5 did test for some very low levels, actually below drinking water standards. So you could actually drink the water. However, but because there was some volatiles in it, we did run it through an air stripper prior to discharging it. So that's on the trailer behind it's a tray stripper, so the water goes in the top, and if you see, it looks like 4 air hockey tables on top of one of another. It goes across each one while it blows a high volume of water up through it, and it pulls the volatile organics off the water and discharges them. From there, it got discharged to the ground surface. So that's just a little aside as we move forward. Prior to starting the test, we had, of course, well number 5, the future groundwater well, and we also had about 7 or 8 monitoring wells. So those monitoring wells were wells in areas. Most of them were residential wells, farm wells, or they were other supply wells owned by other water suppliers. So what we did was we put monitoring devices in those wells, and we surveyed all those points to mean sea level elevation, and we started collecting groundwater elevation data, both to see how the system reacted when well 5 was not being used to other water uses in the area and other water supply wells, and also to determine water trends, background trends of the aquifer prior to doing the test. Prior to doing an aquifer test for the DEP or SRBC, you want to see a declining water level, declining in the wells in the aquifer. So in times of high precipitation, very wet periods of the year, you really don't want to conduct an aquifer test. So we watch all those levels in those wells, and we look for a time when it's declining. And it's kind of tricky because you don't want heavy rains right prior to the start of the test or during the test. So not only do you have to have a declining condition, you also kind of have to be a weatherman and forecast what's going to occur, in the 5 or 6 days, while the test occurs. And beyond that, it's nice to not see any rain during the recovery period when the pump test is over and the well is turned off. So well number 5 we had installed, and we had a series of observation wells. We did see impact in some of the wells, and some of the wells that penetrated the same aquifer as well number 5, we saw larger impacts further away. And some of the wells that did not impact the aquifer or did not intersect the aquifer with as large an interval as well number 5, we saw less impacts closer away. So go ahead. So to start, we had a background monitoring in place. We're monitoring background conditions. We're waiting for a declining water level condition. We're waiting for a time when we're watching these wells and the water level in the wells is dropping. When all that is occurring and the weather looks favorable, we do a step test on the well. So it's a constant rate step test. So we pump the well for three intervals: one at 400, one at 600, one at 800 gallons per minute. In this instance, we pumped it for about 2 hours per step. We pump it until we see like an asymptotic curve develop. So we see the drawdown, and then we see the specific yield of the well kind of equalize, and the curve will go horizontal. When that occurs, we go to the next step. From that data, we found a specific capacity of the well was about 20 gallons per minute per foot. The graph to the left shows you the 3 steps in the best fit line. And from that data, we determined the transmissivity of this aquifer was about 4,400 feet square per day. So after we have that data, that's the data we really use to pick the aquifer test rate for the pumping test. So from that data, we picked 600 gallons a minute. So the aquifer test, per regulatory guidelines, has to be 72 hours. This aquifer test we completed for 93 hours. The reason being is that at the end of the test, I believe the last day of the test, we actually had a fairly significant rainfall, which kind of threw a horseshoe into our test and calculations. So what we did when we had that rainfall is we had a rainfall, and we were monitoring surface water and well water. So we really used the surface water to determine when we came back to a base level. So the rainfall occurred, and we had a weir and a stream, which I'll show you a little bit later. But when the rainfall occurred, we could see that recharge to the stream increase. When that occurred, we kept the test running at a constant rate until that water level going through that stream weir, that volume of water, it rose up after the rainfall, and then it slowly dropped down to the same level it was prior to the rainfall. When that water level got back to the same level that it was prior to the rain event, that's when we started our 72-hour clock again. So basically, it added about 11 hours to the test. But we were in close contact with the regulatory agencies as we did that to make sure that we covered all the requirements of the test and had an accurate test. So in addition to well 5, we did monitor 7 wells in 1 surface water location to help determine impacts of pumping well number 5. Right in front of you here is a cross section of the well. You'll see a couple of the monitoring wells, well 2, well 3, well 1, and the pumping well is well 5. See a little more information on well 5. That's because we drilled it. We had more information on it, which is another challenge with doing some of these this aquifer testing is that some of your monitoring points are farm wells and residential wells. You don't always know a lot about them. Sometimes you can get the amount of casing that's in the ground, the amount of steel casing that's in the ground. You can get the depth. Some drillers' logs will have where they hit water at, but they're not extremely technical on how they're logged. So there is some interpretation you need to do when using some of these observation wells. But they're very worthwhile, and it's very expensive to drill a bunch of observation wells as well. So whenever we do a supply well and a pump test, we'll look at what type of monitoring points we have available to us in the form of residential and agricultural wells, and we'll try to use those to the best of our ability. In some instances, when we don't have enough wells or enough information to look at time distance drawdown curves between points, we will in fact have to come in and drill monitoring points for aquifer test. But that's what we have here is well number 5, which is the test well. We do on this cross section show the geologic contact between the Zook's Corner and the Buffalo Springs Formation, both carbonate formations, which is very good secondary porosity for groundwater wells. But at the same time, these carbonate formations sometimes are very bad for like non-point source and point source contamination and impacts from the surface. All right, so this is the cross section along strike. So along strike will be along the bedding of the rock is what that means. So I talked a little bit earlier about these observation wells, and some of them are fully penetrating the aquifer that we're testing, and some of them are partially penetrating the aquifer that we're testing. So for instance, well RW03 was 292 feet from well number 5, so it's fairly close to well 5. And we only saw 5 feet of drawdown. However, well OW01 monitoring well was 1,392 feet from well number 5, and we saw 8 feet of drawdown. Both wells were along the geologic bedding of the rock, which you would expect more drawdown at, but we had 8 feet of drawdown 1,400 feet away, and we had 5 feet of drawdown 300 feet away. The reason being was that RW03 didn't fully penetrate the aquifer that we were pumping from. So things like that are where we benefit from having a lot of monitoring points and a lot of data to try to weed through some of those gaps in the data and some of those questions. In front of you now is our drawdown graphs for RW4 and 5. Both wells are similar distance from the pumping well. Both have very similar curves, which is good data, which helps match the conceptual model. You'll see that well 4 had a lot of noise, a lot of ups and downs. It's because I believe 4A was actually a agricultural well that was being used. However, with that use, we can still look at that curve and still get the general trend, which is what you see from the yellow and in the blue boulder lines. So from the aquifer test, we develop a hydrogeologic conceptual model. From that model, we found that the testing demonstrated that greater drawdown is exhibited along strike than across strike. So what that means is along strike is along the bedding of the rock. Across strike would be across the bedding of the rock. So it's called anisotropy, and what you expect is if you see layers of rock, if you're driving down the road and you see a road cut and you see the horizontal layers of rock, what that basically means is that the water is going to flow easier along those layers of rock than it will across them, which is exactly what we saw at this aquifer test. And we saw that difference to be about 200%. So the well would draw, the water would draw down about twice as much along strike as it would across strike. So on a small scale, the influence of this strike versus cross strike flow complicates the interpretation of drawdown data. But again, with the more monitoring points you have, the more you can kind of model that and see what's going on. And then as you look at a larger area, the influence of well 5 can be viewed on a two-dimensional anisotropic, as a two-dimensional anisotropic aquifer. So what that is you're basically looking at it as a larger block. You're basically looking at all the fractures and the bedding and everything together, and not, you know, not just two well points and saying, well, this happens here and this happens here. You know, then it does become very complicated trying to draw a conclusion from that. But because we had 7 points on a larger scale, you know, we could look at it, you know, on a larger scale basis. And what we found was, despite the changes in lithology and several faults, and what that means is there are several faults in this area, which would either serve as groundwater recharge or groundwater no-flow boundaries. And there are several different rock types. Where I showed you before, the Zooks Corner and Buffalo Springs met each other. Sometimes a change in lithology will represent an area where you may receive less water to that area, or you may receive more water to that area. With that, we still really saw no boundaries in the amount of water flowing to the well throughout the test. So that makes it more of a complicated model, and like I said, a lot depends on the fractures and the way the rock's broken, things like that. But basically, the model kind of worked, although it probably shouldn't have, but it did. So all these factors together indicate that the hydrologic conditions in this area are fairly complex, and they're probably more complex than the hydrogeologic conceptual model that we used. So to back out a little bit, that was the groundwater portion of it. That's what we're looking at from impacts to water supplies, impacts to wetlands. As it ties into that, we also look at the surface water as well. How drawing the groundwater down below surface water is connected to surface water. So we like to see if we operate a well, if we're going to have negative impacts to maybe the headwaters, to streams, or to wetlands, things like that, and have ecological impacts. So what we do is wherever we determine there's a stream or a wetlands or a pond flowing through our project area or through a potential area of impact, we construct a weir, like the one you see in front of you, a V-notch weir. So the height of the water behind that weir, so if you see that white pipe behind it, that's a stilling well. That's measuring, there's a transducer in there, a pressure transducer, which measures the level of the water behind that weir to the top of the page. That's giving you the amount of water coming through that V-notch weir, which is a corresponding volume for every increment of length above the bottom of the V-notch. So what we can do is we can get data every minute, every 30 seconds, however quick, as fast as we would like it, and we can see the change in the water through that weir. So like the wells, we started collecting background data in this weir a couple of weeks prior to the aquifer test starting. And again, we want to see the water flow decreasing through that weir at the start of the test. And we would prefer to see it decrease through the entire test, and why we collect background data. Again, that's not really what happened. We had a rain event right at the end of this test, which was not a bad position to be in because we collected most of the data up to that point. But again, when we had that rain event, the water in that weir actually topped the weir, went over the top of it, and we waited till the water came back down in that weir until we got to the same level as that prior to the rain event. Some of the challenges with aquifer testing and things like this that are temporary but need to be exact and are difficult is these things need to be built as temporary structures, but they need to work correctly. So when you're collecting background data and you have thunderstorms every 3 or 4 days, you can imagine you can bowl these things over and break them and turn them over and shortcut around them. So they can be a fine line between how much effort you put into it and how it works, to it failing constantly. So it is challenging building these things, making sure they work and they do their job. And like I said, you really can't go dam off a stream and pour concrete, but like I said, they have to work. In this instance, we did have numerous occasions where we had rain events and it short circuited, and I'll show you the next slide, and we had to go back and repair it. And then once we repair it, we had to kind of take that data out where it had failed and then draw a line between it. But that's pretty standard operator procedure when doing this type of work and these type of tests. So here's the data from Weir 1. You can see the precipitation events in the yellow bars at the bottom. You can see the start of the pumping test, the end of the pumping test is a dashed vertical lines. You can see the step test back at the beginning. And like I'd said talking about the last slide, the Weir did fail a couple times. But the long and short of this slide is that once we took out that failed data and continued watching it, we really saw no impacts to surface water from pumping well number 5. And we can pretty much say that definitively because, one, we had no impacts to the surface water flow through this Weir. And 2, just based on well log data and well data from other wells, we did have separation from the first groundwater and surface water. Distance time drawdown data. You're looking at the time drawdown data for OW1. OW1 was the one that was, I believe, about 1,400 feet away from the pumping well. So what we do is we look at the drawdown at the end of the aquifer test. We look at how it draws down during the aquifer test, and then we project drawdown into the future for a couple of reasons. Look at potential impacts. Look at potential impacts to the ecology. Look at potential impacts to other well users. So you'll see from this well that I think projected drawdown for OW1 after 90 days of pumping will be 14 feet. So similar values were observed in wells 3 and 5. And wells number 6 and 7 did not respond to pumping well 5 at all. That's because wells 6 and 5 were across strike. They were across those layers of rock. So we really didn't see a response from pumping at that distance across layers of rock. So with this data, again, we saw a transmissivity of 4,700 feet square per day and a storage coefficient of 0.0004 for the test. So that was data collected and analyzed for what was occurring during the test. We also take the data when from the second the test is shut off, and we look at how that water flows back to the wells, the recovery of the wells and of the monitoring wells. We also use that data to again predict transmissivity, storage coefficients. With that, we looked at well number 2, which is another well that's operated for a public water supply well. And we monitored that for 79 hours, 80 hours, about 2 weeks, about a half a week after the test was over. And with that, we saw that well had recovered 91%, and that's how we generated this curve, which gave us, again, a transmissivity of 5,300 feet square per day. With that, what you have in front of you is a distance drawdown curve along strike and a distance drawdown curve across strike. This kind of demonstrates the anisotropic aquifer, how water flows to the well from one direction versus how water would flow to the well from the other direction. So the top line is drawn through wells that are along strike, along those layers of rock, if you will. So OW1, well 2, well 5, they're all along that layer of rock. So that curve is based on the data from those wells, and that shows you the drawdown. That shows you the drawdown along strike of the well, and how the drawdown is going to be greater than across strike. So wells 3, 5, 4A, and 7 are all across strike, across those layers of rock. And as you can see from this this distance drawdown, the wells are parallel, which is what you would expect, and the data points for these wells fall in the same line. So the data is good. It's exactly what you would expect for this type of aquifer. Cone of depression. This just shows you how far we're drawing water from the aquifer test. So this is at the end of the pump test. So this is after, I believe, what was it, 93 hours of pumping. And this is the 1 foot contour on the end. You would expect to see a foot of drawdown. And then in closer to the well, you'd have about 5 feet of drawdown. All in all, fairly negligible for pumping, 700 gallons a minute. If you look at the scale at the top, 0 to 2 miles, so it's a fairly large impact. So we look at the impact, and you can see just from the topo map and the streams that we are going across some of the headwaters, the streams. So these types of things are a concern from an ecological standpoint when you look at an aquifer test. And they're the type of things we're trying to determine from this is how far reaching is this cone of depression, and will it have impacts? And like I said, this is fairly negligible. We really saw no connection between this and surface water. This is the cone of depression projected after 90 days. You can see quite a bit larger. But the amount of drawdown, the 2 feet, 5 feet, 10 feet, is fairly negligible amount of drawdown as you move away from the well. And as you can see, we're talking about the anisotropic aquifer. The large oval, the length of this is along the layers of the rock. So from kind of northeast to southwest, if you will, that's the strike of the bedrock. That's how the rock's layered. And then for sort of northwest to southeast, the other direction would be along strike, along the layers of rock where it's very skinny, where 2 feet to 2 feet come close together. That's really, so it's drawing water from left to right, not so much up and down. During this whole test, we're constantly collecting groundwater chemistry for a couple of reasons. One, see what the groundwater chemistry is for treatment concerns. Two, if chemistry changes, it may potentially mean that where we're getting the water from is changing as well, and the source of the water is starting to change. So we may be starting to draw in water from a different aquifer, a different lens in the aquifer, a surface water source. So I think every 30 minutes or every hour during the test, we collect temperature data, turbidity, conductivity, and pH. At the end of the test, we graph that. We make sure there's nothing kind of screwy going on. We don't see an abrupt change in turbidity or an abrupt change in temperature. If it would rain very hard and all of a sudden we would see a spike in the temperature, then that maybe start to be an indication that possibly surface water is impacting this aquifer, because we are seeing an increase in the water temperature. So we collect that data throughout the test. When the test is complete, we figure the well has been adequately purged, and we take a water sample for treatment concerns. So we take a large suite of analysis to complete the engineering to do a water treatment facility. That's not what you see in front of you. That's a whole list of data that we collect at the end of the 93 hours. Water level number 5. So sum it up, the water level at the end of the pump test was 405 feet mean sea level elevation. So the uppermost water bearing zone in the well is at 350 feet. So this is from sea level going up. So the fact that the water in the well was at 405 feet and the uppermost water bearing zone was at 350 feet is a good thing. That means we're not drying up that uppermost water bearing zone in the well. You start to become concerned typically when you know where that uppermost water bearing zone is, say at 350 feet, and you draw the well down to 340 feet. At that point, you've lost a water source. Not only have you lost a water source, you're starting to dry something up that water bearing zone may be connected to out away from the well. And possibly that's connected to a wetland or a stream headwaters. So when you're over pumping the well, you typically will pump it down below that uppermost water bearing zone and dry that up. And then when you do that, you've probably pumped it too much, and you'll have a failed test, which occurs a lot. I mean, we do a lot of tests and start pumping it, and we'll pump it for 72 hours. At the end of that, and realize that the well it doesn't yield that much. And with that, we'll take that data and pick a different pumping rate or a different volume to use the well at. So again, after 90 days of pumping, extrapolated those curves, found out the water level in the well would be 399 feet, still close to 50 feet above the uppermost water bearing zone in the well. So that was good. So therefore, it was our determination that the well number 5 could safely be pumped at 600 gallons a minute for an extended period of time without dewatering the uppermost water bearing zone and impacting other wells. So in conclusion, we had no impacts to other surface water tributaries, not by the data we collected or by the water levels in the wells and the data we had from drilling wells and observation wells in areas. Second conclusion, well number 5 was in fact in the same aquifer as well 1 and 2. That's what we expected. Based on the drawdown curve, and all those wells plotting on the same line of drawdown during the test, further confirm that. And third, the aquifer does in fact behave as an anisotropic aquifer. In other words, water does in fact flow along those layers of rock easier than it does flow across them. And pumping the well at 600 gallons a minute will draw the well down about 34 feet at the end of the test and 39 feet after 90 days of pumping, which is, again, 50 foot higher than the uppermost water bearing zone. So not causing any real impacts to that uppermost water bearing zone and hopefully anything that may be connected to that. So with that, the well did get reviewed. Aquifer testing got reviewed by the Susquehanna River Basin Commission and the Department of Environmental Protection in the state of Pennsylvania. They get approved at 577 gallons per minute. Not 600 gallons per minute, just at that volume and at the intervals we were taking water level measurements. That became the average water pumping rate that we determined it was pumped at. It's hard to tell at that volume. We don't have real sense. We have calibrated instruments to figure out these volumes, but just depending on the interval you take the rates, that's what we came up with, which was a good rate. No problem with that, but it came out to 577 rather than 600. Combined withdrawal limit for wells 1, 2, and 5, 1 million gallons a day. That's the combined. Each well is permitted to pump more than that. So if one well would break, it gives us flexibility to operate, the other wells or well at a higher volume to supply the system while we repair a well. Or if one well will become contaminated, it gives us the flexibility to use those other wells at a higher rate. And 1, 2, and 5 are kind of in the same general watershed, although in separate sub-watersheds. The other 2 wells are in more discrete watersheds, separate from 1, 2, and 5. So that gives us that flexibility for both contamination and maintenance that you like to have in a public water system, to have redundancy. And that's why this is a great water system. We have redundancy 4 times over, so really in a good spot to be as far as a water supplier. You're really, we could lose a couple sources for a couple different reasons and still be in great shape to supply everybody. Which when you're designing well fields and water systems, that's where you want to be. Again, the total system withdrawal for all 5 wells, 1.65 million gallons per day. Not quite twice what is needed, but it's close. And again, each well individually can pump much more than that, but that's kind of a system cap overall for the two main watersheds what we can pump. So that's where we want to be. It was a great well. It was a huge success. Being in the Groff Memorial Tree Park was a perfect spot for it. I really didn't touch on that at all. Charlie, the next presenter, will, but whenever you develop a well, you got to have a certain amount of well protection area that you can't put any hazardous materials on, any controlled materials on, any fertilizers, stored petroleum products, stored chemicals. which is why, how we got this presentation and why we're here tonight. It's in the Groff Memorial Tree Park, passive park. We have that wellhead protection area, which I believe in this instance is 200 feet. Really can't say that it limits contamination entirely, but it's what's called for. It's there, we have it, and it's a great place to put a well. That's why it's there. So that's it. Thanks a lot. Wait till the end for questions.
Thank you so much, Jeff. We really appreciate that in-depth look at setting a well and the aquifer testing. Really fascinating. I would love to introduce our next speaker tonight, who is Charlie Miller from Charles D. Miller Consulting. Charlie has 40 years of experience in projects related to civil and environmental engineering. His background includes degrees in chemistry, geophysics, and civil engineering. His focus is on design and construction of best management practices, BMPs, for urban runoff. These have included biofiltration systems, integrated landscape measures, and constructed wetlands. In 1997, Mr. Miller founded Roofscapes, Inc., now Roof Meadow, to introduce green roof methods in the US. Mr. Miller pioneered many green roof techniques that are now in wide use. He also edited the first Pennsylvania handbook of best management practices for developing areas in 1998. We are thrilled to have Charlie here to speak with us tonight.
Thank you.
Thank you, Charlie.
So this is the context for the placement of this well. Groff Memorial Park is a public park and a native plant arboretum, and it's located at the intersection of Conestoga Street and Railroad Avenue in the borough of New Holland. A trust was created to administer this park. The Groff Memorial Trust Park has two objectives as set out by John and Betty Miller. And one is to create a place for passive enjoyment and recreation. And the second is to be a source of education for native trees and plants in Pennsylvania. In addition to providing a permanent open space and an opportunity to observe native plants, the park is also a great complement to the New Holland Memorial Park, which is on the opposite side of town, where the band shell, the tennis courts, the pool, and active recreational facilities are housed. This particular area, because of its mission, was an obvious location for a well. The location of the park and the well was originally a wooded area, lowland with a creek and a broad floodplain. But for a couple hundred years, this area has been used, we believe, primarily for pasturing and meadow. The land is, the soil is wet and the bedrock is shallow, and there's little evidence that the area has been cultivated actively. Beginning in 1980, John and Betty Miller set about to restore this area to being a native forested wetland. That process involved first a donation of 2.6 acres to the borough for the purpose of creating a public park. And then the park design and its construction was funded by the Millers. The Groff Memorial Park Trust was created to fund the ongoing operations through an endowment to safeguard the mission of the park and to administer and oversee the budget and maintenance for the park. The park was dedicated in 1990 in memory of A.B. Charles Groff and Edna P. Groff, the parents of Betty Miller. And here you can see the picture at the dedication, John and Betty Miller with their grandchildren, and Charlie and Edna Groff. This is a remarkable picture because it demonstrates the power of nature to reclaim its own. It also demonstrates that Pennsylvania wants to be a forest, and we'll come back to forest if you give it an opportunity to. And thirdly, demonstrates the vitality of the native trees that were originally part of this landscape. These two pictures were taken exactly 30 years apart, probably within a few days, and from identically the same location. There are over 65 tree varieties in the park. The trees are actually planted in a forest configuration. Some of the trees are more isolated and serve more as specimen trees, but by and large, the trees are intended to create something which is as close as we can come to a facsimile of what a native forest may have looked like in this location in the past. We include a lot of edible plants, which were important in the early history of the colonies. Pictured here is a high bush cranberry, pawpaws, persimmons, serviceberry, and nanny berries. All actually quite delicious fruits, which can be sampled in the park. There are many flowering plants, and intentionally the plant trees were selected so flowering would occur over a long period of time. And there is a flowering schedule for those people that want to see the park at different times during the flowering period, and I'll show you where that schedule is located shortly. So this is a map of the park showing the location of the trees. This map has not been recently updated, but it gives you an idea of the scale and the distribution of the trees in the park. Shown is the location of the well with a red dot and the 200-foot wellhead protection boundary around that well. And in blue, an area which is where with the future site of the pump house and filtration facility will be located. And you can see from this that the park in and of itself is not sufficient to satisfy the 200-foot well protection boundary. And so for this reason, the borough annexed an adjacent piece of land in order to complete that wellhead protection zone. So this is a new piece of public land immediately adjacent to Groff Memorial Park. This annex will increase the wellhead protection area by about 2 acres, or 75%. The soils there are floodplain soils, and the area has been in probably pasture for hundreds of years. This particular piece of property is not part of Groff Memorial Park and is not administered by the Groff Memorial Park Trust. So this leaves open the question of what will happen to this property as we go forward. So the obvious options in this case would be to extend the native plant arboretum that is Groff Memorial Park and incorporate lowland trees appropriate for the floodplain and facultative meadow pollinator plants also that would be appropriate for that part of the landscape. Alternatively, the area might be landscaped in non-native plants, and of course it would have to be managed organically because of the requirements of the SRBC. And finally, it could simply be mowed. It can no longer be pastured because cattle can no longer be run on this property, but it could be mowed. And of course, maintained organically as well. So residents of New Holland that have an opinion about public land in the borough, and particularly this piece of property, I would encourage them to contact the Borough Council, and here on the slide is contact information for the Borough Council President. Just going to briefly show you around the website, which is where a lot of the educational function of the park is provided. So if you go to the website, some of the things you'll find right away is a list of all the plants. And if you click on any one of the trees, you can get information on that tree.
Charlie, sorry to interrupt, but we're not able to see the screen with the website on it.
Oh, that's terrible. Well, then I encourage everyone to go to the website. And on that site, you will be able to access information on every tree. And there's also a virtual tour there, which allows you to do a digital tour of the whole park and get views of the park without actually having visited there, and information on the areas. And of course, an opportunity as well to join and participate as a volunteer. So the park continues to grow and to evolve, and as it does so, it confronts continuing challenges which make it interesting. One is the soils are alkaline based upon the karst carbonate rock, bedrock that Jeff was just discussing. The depth of bedrock is very variable, making placement of trees and consideration of habitat more complex. And there's a continual battle against seeds that are still viable after 30 years in this old pasture, and seeds which are being blown in all the time. The park would not be able to be what it is today without hours and hours and energies provided by many people, including Terry's Lawn Service, which does the mowing and general maintenance, Earthbound Artisans, which is a organic landscape company, Jacob's Tree Service, which does a thorough assessment of our trees every year and does major pruning and occasional new plant installations. Friends of Groff Park are those folks that come to join us, usually through the website, and I'd like to call special attention to Cheryl Schultz, who has been the mainstay of the program for 4 years. Local groups have been, very important, and their services are very much appreciated, and in particularly the Grace Family Church of the Brethren and the Blue Ball Church of the Brethren. Here you can see a picture of the Blue Ball or Grace Family Church folks working on the bridge which goes across the water feature. And finally, Morris Arboretum of the University of Pennsylvania, which donated their professional services to do a detailed evaluation of the park, the collection, and assess its management plan, and also provided recommendations for new plantings in the park as well as in the adjacent annex area. And that's all I have. Hello?
Thank you so much. We really appreciate it, Charlie. Fantastic presentation, both Charlie and Jeff. We do have just one moment here for maybe 1 or 2 questions before we wrap up our presentation tonight. In the meantime, while you're putting your questions in that Q&A box at the bottom of your screen, we do just want to remind you that we want you to take the Lancaster Water Week Pledge if you have not already. That way you can pick up your Water Week Pledge Kit. We do still have 3 more pickup locations this week. And we encourage you to attend our other online lectures. We have 4 more this week, and all of our lectures are going to be recorded. We just ask that you register so we can make sure that we send you the recording after the fact. So now let's see if we have any questions here. We have a question from Julie. She would like to know, what are some common ways that public wells become contaminated?
Yeah, thanks, Julie. There's a lot of ways. Oftentimes in Lancaster County, it's from non-point contamination. So really 2 really broad terms are non-point and point source contamination. Non-point would be from things like agriculture, nitrates, fertilizers. Thanks, Kyle. Mm-hmm. So that would be one of the ways contamination occur. However, those things are generally planned for a little bit because you kind of expect those things to occur. The other one is point sources like gas stations. All of a sudden you have a leak, and one day you wake up and there's gasoline in your water. That is what tends to shut a water system down very quickly. So they're the 2 things, the 2 real general types of contamination. So that's typically what we see in Lancaster a lot, are generally like gasoline stations and then like agricultural contamination.
Thank you so much, Jeff. I have a question from Nick. What is the typical lifespan of a well once it's installed?
The well itself, if installed with good materials, I've seen wells in service for 80, 90, 100 years. What happens is the steel casing they put in the ground generally tends to rot and start to rust, like any metal would rust. When that occurs, sometimes you start to get surface water that impacts the wells, because that 80 or 100 or 200 feet of steel casing is installed in such a way that it keeps the surface water from coming into the hole, the well hole, the borehole. So when that rusts away and that becomes compromised, sometimes the well needs to be abandoned because that steel casing went bad. However, if it wasn't for, the failure of man-made materials, the hole in the rock would really last indefinitely.
Going back to that original question about contamination, are either of you able to kind of comment on, maybe the possible contamination from fracking that might occur in a wellhead area?
Well, in the specific area, for New Holland, no fracking really occurs. So in that area, that would not be an issue. And to answer your question, no, I really can't speak the impacts from fracking on public water supply wells that would occur in that type of region. That occurs. It doesn't really apply to something like this. I really couldn't comment on any real quantitative answer to that.
Okay. And I do just want to let everyone know that we will make sure that the link to groffmemorialpark.org and the incredible tour and educational resources that Charlie mentioned earlier are included. We truly want you to be able to go and explore Groff Memorial Park and get to experience this arboretum and how it's protecting the wellhead and the water supply for New Holland Borough. With that, we have run out of time for today. I want to thank Charlie and Jeff again so much for being with us tonight and for sharing this incredible project. We will have a recording of this available, which you will receive in the next 2 days here. And again, I want to also thank our Lancaster Water Week sponsors who make these events possible. We truly appreciate each of our sponsors for the contributions that they make to keep our rivers and streams clean. Thank you to everyone tonight for joining us, and we hope you will join us for the rest of our presentations this week. Thank you so much.